The first and simplest part of any matrices problem is identifying its dimensions. This is the number of rows by the number of columns. For example, this matrix has 2 rows and 3 columns, making it a 2 by 3 matrix. Addition between matrices is also very simple. The first things you check are the dimensions of the matrices. In this example, you have a 2 by 2 matrix and a 2 by 3 matrix. Because these two matrices do not have the same dimensions, they will not add, resulting in a solution of not possible. In this example, you have a 2 by 2 matrix and a 2 by 2 matrix, so these matrices will in fact add together. Just like with regular adding, the order of the matrices doesn't matter. To add matrices, you find the sum of each corresponding number of each matrix to find that corresponding number of the solution matrix. Once you have done this with each number of the matrices, you have found your solution. Subtracting matrices follows the same rules as adding matrices. Now move on to multiplication. Just like in addition and subtraction, the first step is to identify the dimensions of the matrices. Unlike with regular multiplication, order of the matrices does matter. Here's why. The number of columns of the first matrix must be equal to the number of rows of the second matrix. For example, a 2 by 3 matrix can be multiplied by a 3 by 4 matrix, but a 3 by 4 matrix cannot be multiplied by a 2 by 3 matrix. To start any matrix multiplication problem, it is helpful to circle each row of the first matrix and column of the second. This allows you to visually isolate each problem you are working on. When multiplying matrices, it's important to only focus on a single number of the solution at a time. Here's an example. To find the upper left number of the solution, you must use the top row of the first matrix and the leftmost column of the second. To find this number of the solution, you have to add the products of the numbers of the top row of the first matrix that correspond to those of the left column of the second matrix, like this. This is repeated until you have found all of the numbers of the solution matrix. Dividing matrices is similar to multiplying them. However, an additional step is required. This introduces the concept of matrix inversion. For this example, we'll invert a 3 by 3 matrix. You start by entering the matrix into the left side of a double-wide matrix with the identity matrix on the right side. Here you can see a 3 by 3 identity matrix. Now to invert this matrix, you have to sort of manipulate this double-wide matrix into one with the identity matrix on the left side. There are an infinite number of ways to invert any matrix, however you have to follow 4 simple rules. Number 1. The most important and fundamental rule of inverting matrices is that you have to work with an entire row at once. If you are affecting any number of the matrix, you have to affect its entire row in the same way. Number 2. You can swap rows. This is relatively simple. Another way of looking at it is that you can shift any row to any position in relation to the other rows of the matrix. Number 3. You can only multiply or divide a row by a constant. You cannot add or subtract a row to or from a constant. For example, you can multiply a row by 5 and divide a row by 5. But you cannot add 5 to a row or subtract 5 from a row. Number 4. You can add the numbers of two rows that share the same column and replace either of the old rows with the result. These four rules are the building blocks to inverting any matrix. This is the sample matrix we'll be taking a look at. The first step will be row 2 to row 1 and row 1 to row 2. This is essentially switching row 1 and row 2. This is to move this first one of row 2 to row 1. The next step is row 2 minus 2 times row 1. And also row 3 minus 2 times row 1. This is to change these two first 2's of rows 2 and 3 into zeros. The next step we'll do is row 2 minus 4 times row 3. This is to change this negative 4 in row 2 to a 0. Now the next step is row 1 plus 2 times row 3, changing the 2 of row 1 into a 0. And finally the last step is to negate row 3, changing the negative 1 into a 1. And finally, we have our completed inverted matrix. And here's the equation to show that. Now that we know how to invert matrices, we can apply that to dividing them. Dividing a first matrix by a second matrix is the same as multiplying that first matrix by the inverse of the second. That's how we can divide matrices when we normally wouldn't be able to. Now you can just follow the same steps as you did multiplying to find the solution. Another common problem you'll find with matrices is finding the determinant of a matrix. The simplest matrix to find a determinant of is a 2x2 matrix. To find the determinant of a 2x2 matrix, you subtract the product of these diagonal numbers from the product of these diagonal numbers. For example, with this matrix, the determinant is 1 times 2 minus 3 times 4, leaving us with negative 10. Finding determinants gets much more challenging as matrices grow in size. For example, this is what you have to do to find the determinant of a 3x3 matrix. First, you want to start with the number in the top left corner of the matrix. Now you can omit all the numbers that share the same row and column as that number, and find the determinant of what remains. Finally, to complete this step of solving the determinant, you multiply that determinant by the number in the top left corner. Now follow the same principles for the middle top number. You will subtract this new number from the first number. Finally, you'll apply these principles to the top right number and add that new number to the number you have just found, like this. A more common problem that can be solved using matrices is finding the area of a triangle. You start by finding the coordinates of the 3 points of the triangle on a graph. You can then set these points up in a 3x3 matrix, inputting a 1 in all of the z positions. Now to find the area of the triangle, you find the absolute value of half of the determinant of the matrix. The determinant of this 3x3 matrix is 18. 18 divided by 2 is 9, and of course the absolute value of 9 is 9. Therefore the area of this triangle is 9 units squared. We can test this method by finding the area of a simpler triangle. Using the standard area of a triangle formula, half of the base times the height, we know that because the base of this triangle is 4 units wide, and it is also 2 units tall, then the area of this triangle must be 4 units squared. Now let's try the method we used before and see if it's consistent with this value. Inputting the 3 points of the triangle into a matrix, we get a 3x3 matrix consisting of 3, 3, 1, 1, 1, 1, 5, 1, 1. The determinant of this matrix is 8. Finally, the absolute value of half of 8 equals 4, the same value we calculated with the formula. A less common problem, yet one still found in other areas of mathematics, is solving a system of equations. We can solve these problems using matrices. Let's start off with this system of equations. 2x plus 3y minus 4z equals 2. 3x plus y equals 7. And x plus y plus z equals 12. We can input these values into a matrix like this. All you have to do is manipulate this matrix using the same rules that you followed during inversion. The goal here is to get a 3x3 identity matrix on the left side. Once you have achieved this, you now know the value of each variable. We can test this by plugging in these numbers to the equations. Another fun use for matrices is using them to decode and encode messages. To encode a message, you first have to change all the letters of it into numbers using a key. The key we'll be using for this is A1, B2, C3, D4, etc., etc. For example, the phrase "it's alive" translates into 9, 20, 19, 1, 12, 9, 22, and 5. Now we can put these numbers into a 3x3 matrix. Because these numbers don't entirely fill up this 3x3 matrix, we can input a random number into the final slot. Now we can multiply this matrix by an encryption matrix. For our encryption matrix for this problem, we'll use 320401512. Once we multiply these two matrices together, we get a solution of 202, 37, 58, 96, 11, 30, 86, 44, 5. And here's the final encoded message written out. As long as you know what the encryption matrix is, you can also decode messages as well. For this example, we'll be decoding the message 117, 45, 18, 112, 45, 19, 200, 45, 50, 88, 15, 22, 156, 58, 33. Now to decode this message, you have to divide a matrix comprised of these numbers by the encryption matrix. As stated previously, you cannot divide matrices, you can only multiply matrices by an inverse. So the next step is to find the inverse of the encryption matrix. Here you can see the matrix comprised of the encoded message. The next step is to multiply this matrix by the inverse of the encryption matrix. Next, we write out this matrix as a series of numbers. Running these numbers back through the number letter key, we find that the decoded message is THESEGOTOELEVEN. Finally, using simple problem solving, we can find that the original decoded message was these go to 11.